Welcome everyone, and thank you for joining today's FTCOE webinar on using objective criteria for bloodstain pattern classification. Today's presenter is Jeremy Morris, with a forensic scientist supervisor with the Johnson County Sheriff's Office Criminalistics Laboratory. So at this point, I'll go ahead and turn the webinar over to our presenter. Thank you.
Good afternoon, everyone. Thank you again for joining the webinar today. I really appreciate everyone taking time out of the day to look at this topic. Something that I've been studying a little bit on, but we've got a lot of material to cover, so let's go ahead and get started. So these are the objectives that we're going to cover today. We're going to look at kind of some common errors associated with using definitions to help drive pattern classification, and then understand how to develop these objective features for classification. We'll look at a variety of different sources, such as fluid dynamics and other aspects of pattern formation. And then the other thing that we're going to discuss is how using this approach can assist in an elimination-based approach to address concepts of uncertainty when it comes to pattern classification. So just a brief little intro to BPA. Really what we're trying to do is we're trying to figure out what story the bloodstains tell. We look at the static patterns, generally it's patterns that are left at a scene, but these patterns can also be left on items that are recovered from a scene, such as weapons or clothing or other articles. We look at the features of those patterns, and then we come up with an interpretation and really answering the question of what happened here, what created this pattern, and in the case conclusion concept, what does this pattern mean in the overall concept of the case? So the question is, what process do we use? And we say, well, we use bloodstain pattern analysis. Well, that is a concept that's not necessarily a process. So I'll kind of pull the curtain back a little bit, and I'll show you what I've kind of called the Morse methodology of BPA. Anytime anyone asks me, what is the process that you use when you do your analysis? This is the pattern. This is the process that I use. The documentation, the classification, followed by the analysis. And then the last step that I always use in my process is the peer review of the conclusions, or the technical review. So this is the process that I use, and you can look through the slide and you can see how I break down the individual steps. The documentation of the patterns, the size, shape, distribution, appearance, and location. And then once the bloodstains tell me their own story through their features, then I start the classification process. It starts out really broad and general, and then I start gathering additional case information to see if I can whittle down the possibilities for the classification. So I'll modify that broad classification if necessary. Once I finalize my classification, then I'll start moving into the analysis phase. That's what I call the case conclusions phase, essentially trying to determine what do these patterns mean in the scope of the case. So most of you may be familiar with, or hopefully most of you are familiar with OSAC, and OSAC has developed a draft method for bloodstain pattern analysis, and you can find it on the OSAC website. And they have broken down the methodology into their own steps. It's very similar to the method that I presented on the previous slide. Observation and data collection, designating areas, essentially grouping what is a pattern and what is not a pattern, classifying those patterns based on observable characteristics, refinement of those patterns based on using task relevant information, and then moving on to what does it mean, which would be the event reconstruction or the case interpretations, and then ultimately the final opinion. That final opinion may be based upon a specific case question that was presented to the analyst. So let's look at this pattern. It's a fairly simple pattern with a fairly simple question. How would you classify that? And this may be one that as we look at it, the classification may seem fairly straightforward, fairly obvious. This is actually a pattern that was presented as part of one of the CTS exams back in 2011. And I'm going to use this pattern as an example of how we can use the definitions to inappropriately approach classification, because this involves some discussions that my laboratory had at the time. So up to this point, when we deal with any published means of differentiating one pattern from another, the primary published means of differentiating various patterns is through the definitions and the terms. So back in 2009, Swigstein published a recommended list of terms and their definitions, and around 2017, OSAC and ASB modified those slightly but largely they're the same. And this is the ASB technical report on terms and definitions in BPA. And multiple people have recognized the same thing, that these definitions for these patterns are primarily mechanistic driven. Essentially, how were these patterns created? So we can look at the definitions for backspatter pattern, drip pattern, and transfer stains. As we read through these definitions, they are all very much the same. How is this pattern created, or very mechanistic driven? So for backspatter, bloodstain pattern resulting from blood drops which can be produced when a projectile creates an entrance wound. Very mechanistic driven. So what I have found is that a very common approach is to have the definitions drive the classification. Well, okay, so what does that mean? So let's look at this pattern again, and how do we use the definitions to drive the classification? Well, here's what our group did in my lab back in 2011. So as we looked at this, someone said, well, that looks like a drip pattern to me. And so someone pulled up the definition of a drip pattern, bloodstain pattern resulting from a liquid that dripped into another liquid, at least of one of which was blood. Thought, you know what, that makes sense. I think that this is probably a drip pattern because I can see this pattern being produced by that mechanism. And then someone else said, whoa, 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 well, look at the definition for splash pattern. Now, splash pattern has been modified a little bit, but back in 2011, this is what the definition was. A bloodstain pattern resulting from a volume of liquid blood that falls or spills onto a surface. And they said, look, you can have like a volume of blood that is at a low height and just kind of poured onto the surface, and you could create this same thing. So do we know if it was a drip pattern, or do we know if it was a splash pattern? So this is how, at least within my group, the definitions were being used to drive classification. And I have seen and heard that approach being taken a number of different ways. So as an aside, the definition for splash pattern was modified a little bit based on conversations that I had at the OSAC level when it talked about falls or spills. And this is the new definition: a bloodstain pattern created from a large volume of blood falling onto a surface. So let's talk about using definitions to drive pattern classification. And this really is a misuse of the definitions. Bloodstain never intended this to be the approach. OSAC and ASB never intended for this to be the approach, because the definitions are simply a how was the pattern created. They don't cover what do these patterns look like. If I were to ask you to close your eyes, or just anybody to close their eyes, and I were to read them the definition of an impact pattern when an object strikes a liquid source of blood, does that automatically create a visual pattern in your eyes? And it doesn't. So the definitions were never intended to describe what the patterns look like and what those features were. The second thing is that this is a top-down process of decision-making rather than a bottom-up process. So it's probably good for us to talk about what this means. So top-down versus bottom-up. A top-down is where you see a larger image, and then you see that larger image before you start breaking it down into the individual parts. So when it comes to pattern classification, it is, here's the pattern. Could it be an impact pattern? Yeah, I think it could be an impact pattern. Or here's a pattern. Could it be a drip pattern? Yeah, I think it could be, based on the definition. So you're starting with the upper tier and you're working your way down. So that's the top-down way of thinking. The bottom-up way of thinking is, let me look at the features first, observing the individual parts before interpreting the image. So let me look at the features. What's the size? What's the shape, distribution, appearance, and location? All of those individual parts. And then using that to determine what the larger image might be. So the top-down process is when you're using the definitions to drive the classification. When you also use this, the classifications really are made without considering all options. And what I've seen is that someone will say, you know what, I think that this could be a drip pattern. Let me go look at the definition. Yeah, I can see that the features that I'm seeing could fit what I would expect to see with this mechanism being described. I think it's a drip pattern. And then at that point, a decision has been made, and they really haven't considered any additional possibilities. So that's the third problem. The fourth problem is that this approach is really susceptible to multiple cognitive fallacies. And we could go through a whole litany of them. I've just listed a few. It's susceptible to confirmation bias, to contextual bias, It's very susceptible to anchoring effect, which is, this is what I think it is, this is what my initial idea was, and that kind of drives everything else that we see when we look at that pattern. So if we go back and we look at the bloodstain methodology that's been proposed by OSAC, you're going to see something here that's also within my own methodology. And that is, one of the first steps is classification of patterns from observable characteristics. So that's how we classify those patterns. We start with the observation, the data collection. The classification of patterns is not based on the definitions of the terms, but it is based on the observable features that you see within those patterns. And they go on to say, quote, classification of bloodstains and bloodstain patterns is the process that utilizes observable characteristics to include those mechanisms that cannot be excluded, resulting in an interpretation. So we see two different concepts here. The first is what drives the classification. It is the observable characteristics. But the other thing is, what approach are we taking? Are we taking an exclusion-based approach, or are we taking an inclusion approach? And an exclusion approach simply means you are looking at everything as a possibility to start out with, and based on objective features or other task relevant information, you start excluding various patterns until you end the process, and you either end up with one or you end up with more than one. And we'll give an example of this later on today. So these are the features, and this is a slide that I show whenever I teach BPA, and I say these are different patterns, and you know that they look different. They have, some of them have somewhat similar features, but most of them have very, very different features. And the reason why they have different features is because we have different forces in play, or different mechanisms involved. Sometimes it's really just different forces that are in play. A pool and a saturation stain really are, the primary difference is going to be based on the target surface features. But we know that these are different mechanisms because there are different features, and we need to just remind ourselves to look at the features first before we start jumping to what the classification should be. And this is that better approach, to let the features drive that classification. This is that bottom-up thinking. Let's look at what the story of the bloodstains tell. What's the size? What's the shape, distribution, appearance, and location? Get all of that objective features first, and then start this refinement process using every pattern as a possibility until we finish our exclusion process. And using a feature-based approach for pattern classification has broad support within outside communities, specifically within biology. We use it in BPA, but the question may be, well, is that a scientific approach to differentiating one item from another? And when we look at biological classifications, yes, it is. So biological classifications is historically based on visual features. Here's an organism in front of me. I want to determine what species that organism is, and I'm going to start looking at various features. And they currently use other techniques in addition to their visual features. So we could look at these examples here, and we could ask ourselves a variety of questions. Is it single cellular? Is it multicellular? Does it have internal organelles? Is the DNA enclosed within the nucleus, or is it free-floating within the cytoplasm? Is there a cell wall that's present? Other external features. When we deal with bacteria, we can deal with the shape. Are we talking about sphere, spiral, rod? We can deal with gram staining. That is another technique outside of visual features that we can use. But this is a very typical process when it comes to classification of organisms. So we'll give an example here, and this here is a picture of the Hawaiian goose. And we're trying to figure out what species this bird is, if we were presented this bird to us. Here is the various classifications, starting with the domain, going from domain, kingdom, phylum, class, order, family, genus, and species. And as this animal is moved from one level down to the next level, you can see that the key characteristics are objective features. And so you look and you say, okay, here's a key feature that I need to see within this animal. If I'm going to say that it is a Hawaiian goose, do I see that objective feature? And if you do, then you continue moving down the process. So biological classification still today uses the objective features. Now, we do have DNA that's coming into play, but it has largely been based on biological visual features to start out with. But a critical component is that those features are objective, that they are objective and they are essential for classification, that you just can't willy-nilly say, well, I don't see that specific thing here, but I still think it is going to be this species. That's not following the proper method, not following the process. So when it comes to the question, where do we start? If we're going to use a feature-based approach for classification, how do we even start this process? Well, fortunately, we don't have to reinvent the wheel. There have been numerous others in the past who've started this process, and I encourage you to read this recently published paper that came out earlier this year on bloodstain classification methods, a critical review, and to look at the future. And I really enjoyed this because it goes through all these different methods of classification and does an evaluation on them, who published them, when it was published, what criteria are used in this classification, and do they use objective features or not. And towards the end of the paper, they have this little comment that said, in addition, some classification methods are better at differentiating problematic bloodstain patterns than others. And I like that for a variety of reasons. One is that it says that if you are using different approaches, you are using different methods. And that's key when it comes to determining the error rates. So if you are using a feature-based approach that is a bottom-up process rather than a top-down process, those are not the same methods. And what that means is they're not going to have the same error rates. So if you use the medium, low, and high velocity spatter approach as your classification, that's going to guide you and may give you an erroneous conclusion. Whereas if you use a different method, that may help you with these overlapping patterns. So the key takeaway here is that your method matters, and different people, if they're using different approaches or different criteria, are actually using different methods for classification. They may say that they're still using size, shape, distribution, appearance, and location, but when you start diving into the different approaches, you can see that they really are different. So several people have contributed to this in the past, and I'll just mention a few names here. Philippe Esperanca over in France. He's kind of the one who, within a number of us, kind of gave us this idea of, hey, let's start looking at the features and grouping these just like what we do in biology. Bevel and Gardner did the same thing in a book that they published, and then more recent, OSAC published a bloodstain pattern process map that is a guide to using features to direct your classification. So we're going to give an example of this. So this here is the full process map. I've got the link here at the top, and it's really difficult to see this process map in this view. So let's go ahead and zoom in a little bit. And what you can see here is it's a series of questions. It's a series of yes and no questions. It talks about the target surface. Is this the target surface? If it is yes, then move here. If it's no, then move here. And then it goes on. And as you look through this process map, it's this series of binary decisions. Do you see these features? If yes, then move to this point. If no, then move to this point. And ultimately, you're going to land at either, hey, you need to stop, or these here are the possible patterns that you can use for classification. Now you can see here when it talks about the absorbent target surface, is that shows that this process map is not suitable for absorbent surfaces. And we're going to talk about that later on when we deal with how to develop these objective criteria. But this here is an example of what this can look like for using objective features to drive your classification. So as we come up with our own, there's a lot of things for us to consider. They need to be guided by concepts of fluid dynamics. We need to consider variation and creation processes, effects of target surfaces, what kinds of case information can we use, what kind of case information is appropriate for classifications, and then deal with qualitative uncertainty. And we're going to break down each one of these now. So the first one, let's deal with fluid dynamics. And I just simply have a question for you. I want you to look at this pattern. This pattern is on the floor. It's on a horizontal surface. And how would you classify that? And as we look through this, we see circular stains. The majority of these stains are circular. They're various sizes. They are in a linear distribution, and we could maybe get some overall things there. But I think what many of us are going to see, or what's a common thing, is, hey, we have some fairly large circular stains in our linear distribution. This is going to be a drip trail. And that is actually incorrect. This is not a drip trail. Because when we deal with the distribution, I think we focus only on one concept of distribution. When we think of distribution, we generally think of the arrangement of individual stains within a pattern. But I'm going to challenge you that distribution is much broader than that. That distribution is also the arrangement of stain features within that pattern. So is there a distribution to the size? Are the sizes randomly distributed? Or can we see a pattern where on one side they're really small, and as we move from one side to the other side, they start getting larger and larger? Or let's deal with the degree of ellipse. Are they generally circular on one side of the pattern, and they increasingly get more and more elliptical? What about the distribution when it comes about spacing between individual stains? It's not just the arrangement of individual stains. The distribution is a much broader concept than that. So when we look at fluid dynamics, we have this concept of liquid jet breakup. And if we were to have a hose and just have a constant pressure behind the fluid that's being projected out of that hose, we would see that column of liquid is going to start breaking up, and it's based on various instabilities that are within that fluid as it is pushed through the air. And that liquid jet breakup is a random process. So it creates smaller droplets of that liquid, but those droplets are not of consistent size. They are of varying size. So here's a picture. On the top is a drip trail, and the drip trail, look at the distribution of size. And we see all of these stains are essentially the same size. And it's because we have a replenishing volume of blood that's coming off of a standard surface. Here it's coming out of a pipette, but it could be coming off of a finger, coming off of an elbow or so. But this is what we often see with drip trails, where the stain size stays the same. Now look at the lower picture. The lower picture is a projected pattern. This is where I just took a pipette and I shot the blood straight out in front of me. And going back to that liquid jet breakup, it broke that stream or that jet of blood into smaller droplets, but they were not of consistent size. So the distribution of size is random. And that is a key factor to differentiate between a drip trail and a projected pattern. Both of them are linear patterns on the floor of circular stains, but there are other features that are based on the concepts of fluid dynamics that we need to consider. So here's another pattern. Let's look at how fluid dynamics can help us out here. And again, this is probably not the best of images, but this pattern is on a vertical wall. And we see a high concentration of stains in the center. And they're kind of in a radiating distribution. They all kind of seem to kind of come from that central area and then radiated outward. We've got some that are downward moving. But if we zoom in and we look at that highest concentration, there's a couple things that at least jump out to me. The first is that overall, the larger stains are generally towards the center of this pattern. And as I get further away from this highest concentration, the average stain size actually goes down. The other thing, when I look at the larger stains here, not all of them are circular. Or even elliptical. I have a number of stains that just kind of have a weird, irregular shape to them. Those two features are going to be critical when it comes to the classification. So let's show a video here. This is a high-speed video of the creation of a drip pattern. And what I want you to see is what the droplets do, where the smaller droplets go, where the larger droplets go, and why some of these droplets are circular and why some of them are irregular. So here we have this blood drop striking, and we can see this very small blood drops fly off screen because they have a lot of energy and it takes them off screen. The larger droplets, though, because they don't have a lot of energy, they just land very close to the parent stain, and some of them never are able to completely coalesce into a sphere. They end up kind of as a dog bone shape. And when they land, they don't make a spherical stain. They make an irregular shaped stain. Additionally, they don't spread out flat. They kind of still stick up on the surface. Those are features that help us differentiate between an impact pattern and a drip pattern when all we see are the stains that are on the vertical surface as we're looking at the distribution of size. So here's another pattern. Again, we have this pattern that is on the wall. It as well is a radiating distribution of circular to elliptical stains. And we can see kind of that fan shape to this. Now, I want to caution, most of the time when we see this, we're like, that's an impact pattern. We've got a radiating distribution of stains. Be very careful of that. You can create a radiating distribution of spatter stains by a cough. You can create it with a gunshot injury. It doesn't just have to be an impact pattern. We kind of get very narrow-minded and get this tunnel vision when we see radiating distribution of circular to elliptical stains. It happens to be an impact pattern in this case, but as we look, again, we consider this feature, is there a pattern to the distribution of features within those stains? We zoom in and we're going to look at this higher concentrated area. What I see here is I see a lot of really, really, really fine stains that are in this small area. And if we were to go look at the broader pattern, we're going to see that as we move further away from that highest concentration of stains, this average stain size actually gets larger. It's the opposite of a drip pattern. Here they're actually getting larger, and those really small stains are very close to the area of convergence. Well, this is based on the concepts of drag within fluid dynamics. And this paper came out a few years ago, and it's a great one. And I think that everyone who's studying BPA should have this paper that's within their library. And when they deal with drag, they go through and list a formula. But the bottom paragraph, I think, is what's key. If a cloud of drops is produced with a given velocity, the larger drops typically travel further away from the region of origin because their delta value is smaller than that of the smaller drops. This phenomenon explains why, for example, in gunshot spatters, the smaller stains are found closer to the area of origin. Essentially, he's saying, answering the question, will drag affect a droplet a little bit or will it affect it a lot? And the answer to that is based on the size of the droplet. So this is why with impact patterns, if you look at that, you're going to see that those really small stains are closest to the area of convergence. And as you move further away, your average stain size actually gets bigger. And that's based on this concept of drag. So let's look at objective features as they deal with variations in the creation processes. So here's an expiration pattern. And we're going to look at the definition of the expiration pattern. It's a bloodstain pattern resulting from blood being forced out by air out of the nose, mouth, or a wound. And here we see this pattern. This is a very typical expiration pattern that we see. We kind of get used to these. We've seen them in our basic training and all. So here's another expiration pattern that I created. I want you to think of the features that you often look for when trying to determine if something is an expiration pattern. And it's probably these four, or at least the top three. And are there bubble rings that are present? Do you have lighter coloration of some stains indicating that they were diluted? Do you have those ligament strands, these lines that attach one stain to another? At our lab, one of the things that I will request anytime I think that we might be dealing with an expiration pattern is I will request our biology section to do an amylase test to see if there's the presence of amylase within that blood that is in high concentrations in saliva. We have to be very careful with these four features because there's slight problem. All of these features are associated with the presence of saliva. The bubble rings is because air bubbles in the saliva. The lighter coloration of some stains is from blood, is because it's diluted with saliva. The ligament strands is from saliva. We train ourselves to look at blood that is coughed from the mouth. But what about blood that comes from the nose? What is that going to look like? Are you going to see any of these features? Because you're likely not going to be dealing with the effects of saliva. What about blood from a sucking chest wound? I've had two of those cases now where I've had sucking chest wounds and the blood stains that come from that. So here's a specific case. This isn't blood that's coming from a sucking chest wound, but this is blood that's coming from a broken nose. And if we were to look at this and we're trying to see, okay, do I see features that help me determine if this is an expiration pattern? There's no bubble rings. There's no diluted stains. There are some that are a lighter coloration, but we're dealing with target surface effects in this one here. There are no ligament strands. And if we were to do an amylase test, the amylase test is going to be negative. So we think, well, does that mean that I can exclude expiration pattern? No, we've got a documented injury of a broken nose. In fact, on this one, you can see actually two separate patterns. You can see a heavy concentration of stains on the left-hand side of the image, but if you go over to the right side of the image, you can also see a second concentration of stains. It's just not as dense, and it's because this blood is being blown out of the nose, where there's more blood on one side than the other. So another thing when we deal with other variations in creation processes, think about a projected pattern. And this is a pretty classic projected pattern. This is actually at a scene. It's not lab generated. It's blood that's created from the ejection of blood under hydraulic pressure, typically from the breach in the circulatory system. And so we see these features and we think, well, what are the features, again, that you typically look for in projected patterns? And it could be these. Do we have a linear to curvilinear distribution? Is it this upside down U or this undulating pattern, kind of a wave-like pattern distribution? How big are those stains? And we think, well, they got to be large stains that are really wide, and many of them are going to have flows. And that's exactly what we have here, this upside down U of large elliptical stains that have flows that extend all the way down to the bottom of this refrigerator door. But again, we have a problem with this approach. Many of those features associated with breached arteries on vertical surfaces. If you have a breached vein that's on a horizontal surface, are you going to see those same features? You're probably not going to see those same features. So here's an example of where my conclusion is that this was a projected pattern that was created not from a breached artery, but this is from a breached vein. And it looks very different than the pattern that we saw before. It is a linear to curvilinear distribution, but the stains are significantly smaller, and they don't have that upside down U or that undulating pattern to them. But I had sufficient case specific information that allowed me to determine that I was comfortable calling this a projected pattern coming from a vein. All right, so let's deal with the effective target surfaces now and the objective features. So here's a pattern. We've got some blood. We see all the blood that's on the tile floors, and we're going to zoom in and look at that a little bit closer. But notice that we're going from one surface to another surface. We're going from a smooth, non-porous tiled floor onto carpeting, which is very much an absorbent and porous surface. And look at what the features look like. They completely change. We have very large circular stains that are on the tile, but immediately next to that, once we transition to the carpet, the stains totally change their appearance. They're no longer really large. They don't look that impressive anymore. They're much smaller. Those stains on the carpet are probably about 8 millimeters wide at most, 5 to 8 millimeters wide. They're not from different mechanisms. It's the exact same mechanism that simply transitioned from one target surface to another. They look differently because the target surface features are completely different. And that's where appearance and location is really important when we're dealing with pattern classification. So the change in the target surface can have a dramatic effect on the features that we see. So we just saw an example of a non-porous versus an absorbent surface going from tile onto carpet. But we can also have the features as we transition from a smooth surface onto a rough surface. That can change the features. We did this in our basic class where we had drip stains and we put it on paper, we put it on glass, we put it on tile, then we moved to brick or wood. And the exact same mechanism, same volume, same height, created stains that were very different. And it's because of the roughness of the surface. Vertical versus horizontal, we do this with the same thing, change the angle of impact for those drip stains, and the features are going to change. Painted versus bare metal. And I've seen this a number of times. If I've got like the stainless steel interior of a lot of sinks, if we have blood on the side of those, they may look like they have a diluted appearance to it, and it's not dilution at all. It's just a feature of that target surface. And also the presence or absence of contaminants on the surface. We've had a number of case examples where we have blood that is in a very dirty kitchen where there's a lot of grease and other food debris, and that changes the chemistry of that surface and the ability for that blood to adhere and stick. So we have a lot of different weird things that kind of go on with how those stains look, and it's because of the contaminants on the surface. Probably the biggest thing, though, is the porous versus the non-porous versus absorbent. absorbent. This really is the biggest change that I see, and particularly when we're dealing with clothing. See, the other thing that we need to deal with objective-wise is case information. So I want you to consider these definitions: back spatter and forward spatter. And remember, these are mechanism-driven definitions. And as we look through these, both of them have a very common theme, and that is they were produced by a gunshot, is what we have. So for me, if I'm going to restrict my classification, I'm going to say this pattern is definitely a forward spatter pattern, or this pattern is restricted to a back spatter pattern, I am required to have a documented gunshot wound. If I don't have a gunshot wound, I may need to consider these for sure, but I cannot exclude everything else and restrict my classification to just forward spatter or back spatter without the presence of a gunshot injury. So classification of forward spatter probably requires evidence of a projectile in the immediate vicinity of the pattern under consideration. And I'll give you an example here. This here is a pattern that I had at a scene. And if you look below, like, well, where's the pattern at? Look below the marker A, and you're going to see a small number of stains. And you think, well, that's not very impressive. This is what a real forward spatter pattern looks like. What we create in our training by shooting bloody sponges is misleading when it comes to what real forward spatter and back spatter patterns look like. And we can have a whole other discussion about that. But this initially was classified as just spatter stains. But if you look above that, we have this rectangular shaped defect that's in the door jamb. And based on the crime scene report, within the wall below this defect, the bullet was found. So this is classified as a bullet hole, and we have the bullet hole that is in the immediate vicinity of spatter stains. Medical reports show that this individual had a gunshot wound to the hand. So because of that, I classified this as a forward spatter. All right, so if we think of other patterns, what other case information would assist in classifying the following things? What would you need to see in order to call a pattern a cessation pattern? What would you need to see to call something an expiration pattern? Impact, insect stain, projected pattern. So if I look through these, for me to call something an expiration pattern, do we have a documented injury to the respiratory system? So is there an injury to the mouth, to the nose? Do we have an injury to the lungs? Or do we have documented blood in the nose or the mouth at the time of the scene? So those are things that I'm going to be looking for. Again, that's objective information that I need to have that information before I restrict my classification to an expiration. For insect stains, if I've got documented insect activity, I have to consider the possibility of insect stains being at my scene. And projected pattern, this is interesting because we think, well, does that mean you have to have documented proof that an artery was breached? And for me, my approach is I'd like to have that, but I don't have to. And the reason why is because my history in reading autopsy reports is they will only document the major arteries or the major blood vessels that have been breached. They often do not have a lot of documentation about the minor arteries and veins that were breached. I've had a couple of scenes where I'm very comfortable it was a projected pattern, but the autopsy report did not specifically state a specific artery that was breached. But there's a couple of critical points here, is that the absence of certain information does not necessarily mean the pattern should be excluded. That's just what we now discuss when it came to projected pattern. But if I have the presence of certain information, that does not mean that all other mechanisms can be automatically excluded. So let's say I have spatter stains, and I do have documentation in the autopsy report that the jugular or the carotid was severed. Well, that doesn't mean, okay, all spatter patterns now are going to be projected patterns. No, it means I have to, at minimal, I have to include projected as a possibility. But that does not mean that I have to call everything a projected pattern. It may very well be that we have spatter stains within the scene that were created by entirely different mechanisms. Projected simply must be included because of that case information. All right, so when we're going to deal with qualitative uncertainty, whatever classification method we come up with, it must recognize the following possibilities. One is that two different mechanisms can create patterns that not only have very, very similar features, they could actually have identical features. And that's based on a lot of different things. Both of them could create a limited number of stains that are on target surfaces that are not particularly good. And we just really cannot tell the difference between them at all. Another is that a pattern may not have sufficient features to limit the classification to a single type. And it's like, yeah, I see features there, but there's just not a lot of information. So the way that I approach it is my classification is based on the quality and the quantity of the information that's present. So I can have a lot of information, but it may not be very good quality, so I can't really do a lot with that. So let's look at this pattern here at a scene. So this is how I document spatter stains on walls that are dark. I use these little circle tabs or reinforcement tabs because it allows the location of the stains to pop up very easily in images. And we can see we have this wide distribution of these stains. These stains are circular to elliptical. They all have downward directionality, if they have directionality at all. And as we look at this, yes, they're spatter stains, but I'm not going to automatically jump to an impact pattern because I can't really eliminate. How am I going to eliminate cessation from this? Because we've got a lot that's going on. We have numerous injuries, especially injuries to the hands and to the arms. We do have some potential impact mechanisms that are going on, but I don't have the necessary features within this pattern, especially when they're all going downward, to comfortably feel like I can eliminate this classification to just a projected pattern. Or excuse me, to just an impact pattern. So for me, this pattern here was simply classified as a group of spatter stains because I had a lot of different possibilities that I couldn't exclude. And the necessity of considering qualitative uncertainties came up in the black box study that was published a few years ago. And if you read the supplemental data, which is a Word document that's like 70+ pages long that has just a wealth of knowledge in there, you find out that the researchers discovered that participants struggled with consistently differentiating between these three patterns that were on horizontal surfaces: drip patterns, projected patterns, and splash patterns. When the known mechanism was available, so it was a lab-generated pattern, participants got it wrong a lot because these three patterns really overlap to a significant degree. So we need to be aware of this. So if we see these patterns that we think, oh, this is going to be a splash pattern, or this is clearly going to be a drip pattern or a projected pattern on a horizontal surface, you need to take a step back and say, how am I going to exclude splash? How am I going to exclude projected if I want to call this a drip pattern? And this paper tells me I may actually end up getting it wrong a lot. So these are the things that drive our objective criteria. So what are the components that we put into that? So here the criteria must be objective. Second, the criteria must be established. Well, what do I mean established? For me, that means they're written into policy, that they need to be written down. So that shows everyone who wants to see my method, this is what I'm using for my pattern classification. And then I really have to resist making exceptions to that criteria. And those are the times where I feel we're really sticking our neck out, where we think, you know, I don't have this specific feature here that that's really needed, but I still think it's this mechanism. So we make an exception. Don't let yourself do that. So I'm going to show you what's in our procedures at our lab. These are the objective criteria that are actually written into our policy. So for spatter stain, we have criteria regarding size, shape, and then we have other comments. So these are on smooth and non-porous surfaces, you know, so walls and such, it seems. Here's the general size, here's the general shape, other comments. And what it means is that you got to have spatter stains in order to call certain patterns. And then so here an example is back spatter pattern. General requires the presence of spatter stains. Well, what are spatter stains? Go look at the objective criteria for spatter stains. Here's the criteria for distribution. Here's the criteria for appearance. Take a look at that. The presence of cerebral spinal fluid may give some stains a lighter color. So that's kind of important to know. That would explain some features that we see. Then look here, a documented entrance gunshot wound is required to definitively limit a classification to this pattern. And then other things may be present: bone, hair, fibers, other ammunition components. So these are the objective criteria that I have for these two patterns. Now, if we look at drip pattern, we've got the same type of thing. We've got some general comments: have to have some spatter stains. They can be on vertical or horizontal surfaces. But if we have a vertical stain, a vertical surface, the parent stain cannot be on the vertical surface because of how that pattern is created. Distribution appearance. So I want you to look at the other considerations here. And the other considerations is that it's going to be difficult to differentiate between drip pattern, splash, and projected on vertical surfaces. If you can't differentiate it, I've borrowed this phrase from Paul Kish: large volumes of free-falling blood. If I'm not sure which of these three it is, that's what my report says: large volumes of free-falling blood. And that's an acceptable classification that includes all three of those mechanisms. So this is how I report it out. And again, this is in my policy. So I've given the objective features for the patterns, and now how do I report that out? So if I'm going to call something, when the features of the bloodstain, the case relevant information are not suitable to limited classification, I either am listing everything that's possible, or I'm doing a broad category. So the spatter stain, the stains on the handgun are either impact or satellite stains, or I simply say that they're spatter stains. So I change my objective criteria when I move from the scene to textiles. So here's our procedures. The features for spatter stains on non-absorbent surfaces are on the top. For clothing, it's on the bottom. I'm just going to highlight one thing here, and that is the appearance. I have specific criteria to call something spatter stains on fabric: that individual stains penetrate into the construction of the textile, and they must be spheres, and they must, so that's what they have to look like. An additional thing, if I'm going to call something a spatter stain on a textile, it has to have the correct size and shape, has to be circular to elliptical. It must penetrate into the construction of the textile. It can't just be on the surface. It has to be driven into either the weave or the construction of the yarns. And I just can't have a few stains in a very small area. It has to be non-localized distribution. Well, what does that mean? It's got to be across the garment. And that's because if you think about when you create an impact pattern or an expiration pattern, how many times is it just on a 3x, like a 2-inch by 2-inch area? It's generally not that. It's across the breadth, across the full width of the garment. So these are requirements that I have. Here is an image that's going to be in an upcoming book. I'm going to put a plug in for this book. This is the Handbook of Bloodstain Pattern Analysis. It's edited by Toby Wilson. It's going to be published later on in October, and this here is a visual taxonomy that can be used for bloodstains on non-absorbent surfaces. And you can see how what it does is it visually shows that you can have the same features that are shared by different patterns. And we're going to look at the lower left oval. Here we have circular to elliptical stains. These are spatter, and then here's various distributions: random distribution, linear to curvilinear, radiating distribution. And if something is in an oval, whether it's a small oval or within the larger parent oval, all of those patterns must be considered, unless you have specific case related information or features that you can use to exclude those. So, and this is the exclusion-based approach. All pattern types are considered as options and can only be excluded based on specific objective features or case information. If injuries are documented that can lend to a specific pattern type, you have to at least consider that and include that pattern type, unless you have objective information that justifies that exclusion. And that exclusion-based approach helps mitigate against confirmation bias. It helps mitigate against tunnel vision, against anchoring, and it's more of a bottom-up approach. So here is what I do at a scene. So here's a pattern. We're going to look at II. We have a linear distribution of circular to elliptical stains. And on the left-hand side is a worksheet that I use. It has all pattern types that are spatter stains. And what I will do is, if I want to exclude something, I cross it out and I have to write down the objective information that justifies that exclusion. Now that can be features, whether it's distribution or appearance. It can also be based on the presence or absence of specific case information. And here, because I know that there's no gunshot injuries, there's no injuries to the respiratory system, I can get rid of back spatter and forward spatter and expiration pattern. But there's two patterns that I can't eliminate one of those. So cast off and projected pattern. I'm like, I can't really eliminate one of these. So my conclusion in my report was at least one linear distribution of of spatter stains. So linear distribution of spatter stains is what I reported this out as. So that's an example of taking an exclusion-based approach. So a couple of take-home points. The method that you use is in any aspect of science is at the heart of your process's reliability. You need to make sure that you are using a good, solid method that has strong foundations. If you don't have objective criteria for pattern classification, you are running a real risk of erroneous conclusions when it comes to your classifications. And there's still a lot more that we need to do in this area. We can still learn a lot from fluid dynamics, stuff that's already published or work that still hasn't been done yet. There's much more that we can learn by actually creating the patterns in the lab. And I encourage you to go and just throw blood around. And essentially every time I throw blood around in the lab, I look at a pattern like, yep, did not see that coming. And that helps me a lot. And the last thing is honor the boundaries that you and the work that you do. Always honor the boundaries. I want to thank you for your time. I really appreciate you sitting in. I hope the information has been helpful. If you want to contact me, here's a couple of means that you can reach out to me, and I'll turn it over to any questions that people may have.
Well, thank you, Jeremy. I am John Grassel with the Forensic Technology Center of Excellence. And again, as Jeremy said, if you have further questions, I know we have some ready to go right now, but if you have any further ones, please type them in now. Excellent presentation, Jeremy. Thank you again.
Thank you.
So our first question, when classifying, do you make a difference between strict feature-based classification and interpretation once context information are considered? And uses an example in this question. If you're looking at forward or back spatter, would, based only on the observable features, characterize as spatter stains. And in a second phase of interpretation, you would add the context info to say that back or forward spatters should be considered. Or do you separate those two phases when you do the reporting?
I do the first part. When you look at my notes, you're going to see a broad classification. You'll see in my notes where I describe all of the features. My notes, I'll say these are spatter stains. And then later on in my notes, you'll see where I have gathered the other objective information. Hey, we've got a documented gunshot injury. And then I'll break down other things. Okay, we can exclude this, we can exclude this, final classification, forward spatter, final classification, gun or back spatter. So I do the former approach. I try and split that up. So that way, when my reviewer is looking at my notes, they can see the chronological thought process that I have.
And speaking of reviewers, Jeremy, do you always have all of your decisions reviewed by a second analyst?
Yes, every single one of my conclusions is reviewed prior to being published. So that is a critical part of my method. That's a requirement, actually, of our laboratory's policy. So what that means when I'm on scene and detectives are there, I don't give them anything. I know it's very frustrating to detectives, and I know that's very odd, but I don't tell them anything because I realize that if I say, yeah, this is a projected pattern, I've now given them a conclusion prior to it going through tech review. So I don't say anything, it seems.
Okay. What type of features within bloodstains do you feel is least understood when it comes to classifications?
I think it's probably the distribution. I think when we are talking about distribution, our minds just stop when we deal with the arrangement of individual stains, and we aren't really considering the other concepts of distribution, the variation in size, the variation in ellipse, the variation in distance between stains. I think we could do a lot better job in understanding the concept of distribution.
Let's talk about the opposite. What features do you feel are overemphasized or misused?
I think when we see radiating distribution, we automatically or we default to an impact pattern. And as I mentioned in the presentation, that you can string an expiration pattern. You can absolutely do that. Radiating distribution of spatter stains does not automatically mean that it's an impact pattern. Impact pattern is a possibility, but there are other approaches as well.
Great. Our next question is it possible that stains can be combined? Now, I know you mentioned that a patent may not have sufficient features to limit to a certain type, but is it possible that you listed in your report as, two distinct patents, but it's one for that stain? Is that even possible?
Yeah, I've had one pattern where I have said that, and hopefully this is answering the question, where I've said that this pattern is an expiration pattern, but there is a possibility that an impact is involved. And the reason being is we had a blunt force trauma to the mouth where the jaw was broken. We had all the features that were sufficient to support an expiration pattern, but I could not completely exclude the possibility that it was instead of a cough, it was a blow to the mouth that created those patterns. So that's how I reported it out.
Thank you. Our next question. Many detectives receive very basic training regarding bloodstain pattern analysis, but they use this limited training to draw conclusions. Is there any documentation or articles that you can think of that would warn against this practice of the detectives or investigators doing this?
Yes, first it goes against best practices. ASB as well as Swigstein published minimum training requirements for anyone who's going to issue a bloodstain conclusion, and it specifically says a 40-hour basic is insufficient. There are also at least 2 published papers out there that show that novices have a significantly higher rate of error when it comes to classification than those who are experts. One of them was looking at a single pattern type, and there was a 44% error rate for novices, and the novices were those who just had a basic, whereas experts, those who had advanced training, were court qualified, had, I believe, a 7% rate of error with a single pattern. And then there was another study that came out of Australia where they looked at their 3 different levels, level 1, level 2, level 3, and the degree of erroneous classifications. And what they found is what we would expect is that if you have very limited training, you're going to get it wrong at a higher rate.
Great. Next question is, a lot of your classification process seems to rely on other information such as a gunshot wound or a bullet in the wall. How do you avoid contextual bias in those cases to determine what is relevant and what is irrelevant information?
Well, you're not going to be able to completely remove context. So if I go to a scene and I see a body there and I see a gunshot in the wall, I've got that information. I've seen it. I've observed it. I write that down in my notes. My notes, when I get information that is outside of the observable features, my notes have the dates on when I saw that. So often I'll say, this is the information I knew ahead of time. And then it's up to the reviewer and others to say, well, how did this affect your conclusions? And again, that's why a tech review is so important, is because you're going to have a second set of eyes that is largely going to be blinded to a lot of that case information, and they may be able to say, yeah, I think you're wrong on this. I think you might have approached this in a biased approach.
Thank you. Unfortunately, we do not have time for all the audience's questions. Anytime that this topic comes up, obviously, plethora of questions, and this has been a great conversation and presentation, Jeremy. Thank you again.
My pleasure.
Please feel free to reach out to the presenter for additional information if we did not have time for your question. Thank you for attending, and thank you again, Jeremy.